Good afternoon all. I am Suchita Srivastav and today we will study about atmospheric trace gases. Atmosphere is a thin and fragile layer of air surrounding the earth. It is mainly composed of two types of gases. One is main gases or fixed gases and the second is variable gases. Main gases are nitrogen, oxygen and argon. These are called fixed gases because their concentration does not vary much with space and time. Like nitrogen is present in the amount 78%, oxygen in 21%, argon 0.93% means their concentration will always be fixed by this number and it will not change with space and time. Remaining 0.03% contains all the other gases in the atmosphere. This is very small amount and it contains more than 1000 gases. These gases are called variable gases. Variable gases because their concentration vary significantly with space and time. Though these gases are very small in amount, few of these gases play very important role in the atmosphere. Few examples are carbon dioxide, methane, ozone, nitrogen dioxide and hydrocarbons. Few of these gases can act as greenhouse gases. Greenhouse gases are those gases which absorb terrestrial infrared radiation and contribute for the radiative budget of Earth. Few gases can act as pollutants. Few gases can act as oxidants. So these are variable gases which vary with space and time but having very important implication in Earth's climate. As these gases are very small in amount, we cannot express these gases in percentage. Like if ozone concentration is in percentage, it is 0.000003%, then it is not a convenient way to express. For that, we use mixing ratio of a gas. Here, Ci is equal to Ni by Nair, where Ni is the number density of a particular gas I to the number density of air. Then Ci will be mixing ratio of that particular gas I. As you can see, it is a unitless quantity. This quantity is expressed in terms of part per million, part per billion or part per trillion. It depends on the amount of gas present. Suppose we are talking about ozone and this ratio for ozone is equal to 0.3 into 10 to the power minus 9. In that case, it will be said that this gas is present in the amount of 0.3 ppb. Other important unit of measuring trace gases is Dobson unit. This is a unit which is in which total column content of gases are expressed. For expressing any gas in Dobson unit, you have to bring all the molecules of this gas present in the atmosphere at surface at standard temperature and pressure. Standard temperature 273 degree Kelvin and standard pressure 1013 hectopascal. Then it will form a layer of pure gas. Thickness of this layer in millicentimeter is the column abundance of that gas in Dobson unit. To understand this, a simple example is given. Suppose all the ozone molecules present in the atmosphere from surface to top of the atmosphere, we have bring all the gas molecules near the surface and it forms a layer of pure ozone of the thickness 0.3 centimeter, which can be written as 0.3 centimeter can be written as 300 millicentimeter. Then it will be 300 Dobson unit because thickness is expressed in millicentimeter. 1 Dobson unit contains 2.69 into 10 to the power 16 molecules per centimeter square. Few trace gases can act as air pollutants. The question is, what is air pollution? The presence of any substance in the atmosphere in quantities which are or may be harmful or injurious to human health, animal or plant life. There are two types of sources in the atmosphere for this sort of air pollution. One is natural source and two anthropogenic source. Natural sources are those sources which are naturally occurred in our earth, like forest fire or volcanic eruption. Anthropogenic sources are those sources which are man-made, like industrial emission, vehicular emission, domestic cooking, crop residue burning, etc. There are two types of air pollutants present in the atmosphere. One is primary pollutant, which are directly emitted in the atmosphere because of any natural or anthropogenic activities. The few examples are given here. These are carbon monoxide, nitric oxide, sulfur dioxide, nitrogen dioxide, volatile organic compounds, particulate matter, ammonia, etc. These primary pollutants can, because of complex chemistry or photochemistry, generate secondary pollutants. Secondary pollutants are not directly emitted. They are produced by primary pollutants and having very bad impact on human health or crop production. These are sulfuric acid, nitric acid, ozone, hydrogen peroxide, etc. Main gaseous air pollutants are given here and their health impacts are also written. Like ozone can cause wheezing, coughing, eye irritation, shortness of breath, nausea, chest pain, increased risk of asthma attack, reduced functioning of immune system, etc. Carbon monoxide can create dizziness, headache, nausea, vomiting, and death. Nitrogen dioxide can create eye irritation, throat infection, wheezing, coughing, tight chest, triggers asthma in asthmatics. And sulfur dioxide can create eye irritation, breathing difficulty, dizziness, inflammation of respiratory system, worsens asthma attack, aggravate existing heart diseases. So in the present lecture, we will focus mainly on ozone and its precursors. Precursors of ozone are carbon monoxide, nitric oxide, nitrogen dioxide and hydrocarbons. All these gases are air pollutants and emitted in the atmosphere because of industrial emission, vehicular emission, biomass burning or domestic cooking. As I already told that these are those gases which are directly emitted in the atmosphere. These are primary pollutants. These pollutants, because of very complex chemistry in the presence of sunlight, creates ozone. So ozone is a secondary pollutant. Once emitted, there are several atmospheric parameters which can affect the distribution of these gases over one location. The most fundamental atmospheric process which affects distribution of air pollutant over one location is atmospheric boundary layer. What is atmospheric boundary layer? Atmospheric boundary layer is the lowest part of the troposphere which directly responds to surface forcing. Like if air pollution is emitted near the surface, within an hour it will be mixed within the boundary layer. However, it can take several days to get mixed up within the other free troposphere. So what defines the boundary layer? The top of boundary layer is there is always an inversion layer. Because of in this inversion layer, temperature slightly increases and this differentiates between boundary layer and the pre-troposphere. This boundary layer is very important for the distribution of air pollutants. Suppose a pollution plume is emitted inside this particular boundary layer, and because earth becomes warmer during daytime, this parcel will move towards the upper side because it is warmer with respect to ambient air, and in that case it will be lighter than ambient air and it will move towards higher altitude. It will move till it finds a layer which is warmer with respect to this. It is similar to a balloon which is filled of hot air. As long as balloon contains hotter air, it will go higher. Similarly, as long as parcel containing pollution is warmer with respect to ambient air, it will move higher. But near in this inversion layer, the air parcel present inside this inversion layer is always warmer with respect to air which is just present just below this inversion layer. So this layer will act as a barrier. It will not allow this air parcel to cross it and go inside the free troposphere. So height of atmospheric boundary layer defines a barrier for the mixing of air pollutants. Height of atmospheric boundary layer varies with space and time. During daytime, boundary layer height is maximum around 12 o'clock to 2 o'clock, and its height is very small during night time. Similarly, the boundary layer height is high during summertime and it is low during winter time. Suppose there is no inversion layer, then what will happen? The example is given in this picture. This is air pollution which is emitted over one location, and there is warm air, then cool air, and then cooler air. So there is no inversion layer. Air pollution will keep on moving towards the higher altitude and it can go up to tropopause. But if there is an inversion layer present, then this inversion layer will act as a barrier and it will not allow this pollution to penetrate through this. In that case, the pollution will be trapped. The lower the height of inversion layer, higher will be pollution trapped below this. And if there is no inversion layer, whatever pollution is emitted, that will keep on moving towards the high altitude and the air quality over the region will become very, very good. So boundary layer plays a very important role for the air quality over one region. During night time, Earth's surface becomes cooler and temperature structure near the surface becomes different. It now near the surface, from surface to around 200 to 500 meter, temperature increases. Again, this is an inversion layer. Because of this inversion layer, whatever pollution emitted near the surface will remain trapped. There will not be any vertical movement. There can be only horizontal movement or forced wind movement. But this parcel is the parcel which is sitting on higher side is warmer, so there will not be vertical movement. So during night time, if the pollution is emitted in the atmosphere, that will remain trapped. So if pollution is emitted in the atmosphere during night time, air quality over that region can be significantly poor. Above the nocturnal boundary layer, daytime residual layer occurs, which is just the remaining part of the vertically mixed layer, and inversion layer also remains like that. Other than local effect, there can be long-range transport of air pollutants. Once emitted, these pollutants can get transported to large distances. Like an example is shown here, where data is taken from MOPIT instrument for carbon monoxide at 600 millibar, and this carbon monoxide varies from 20 to 440 part per billion. This plot is for 5 consecutive days, March 10, March 12, 13 and 15, and this shows that over this location, China, a pollution plume of carbon monoxide emitted, and within 5 days it got transported to Northern America. So it is not necessary that a place will be polluted if and only if over that location the pollution is emitted. It is also possible that the region where this pollution is not emitted, it can receive pollution from upwind locations. So monitoring of upwind location air quality is also very important. A very good study shows that increasing pollutant emissions from emerging economies like China are responsible for a springtime ozone increase in the free troposphere over western North America. So continuous emission over upwind location can significantly degrade air quality over the downwind location. When we want to study long-range transport, you should have consecutive data at the same time data all over the globe. That data can be provided by satellite only. Few satellite instruments are introduced here. One of them is MOPIT, Measurement of Pollution in the Troposphere. It is an instrument on board Terra spacecraft. It is a nadir viewing instrument. It senses upwelling terrestrial infrared radiation at 4.7 micrometer and 2.2 to 2.4 micrometer. It provides total column content of carbon monoxide and its vertical profile. MOPIT level 3 product provides global distribution of carbon monoxide at 1 degree by 1 degree horizontal resolution. And this data is available since March 2000. Another instrument, ozone monitoring instrument. This is an instrument on board Aura spacecraft. It senses Earth's backscattered radiation between 264 to 504 nanometer. It provides total column content of several gases like ozone, nitrogen dioxide, sulfur dioxide, etc. OMI level 3 product provides global distribution of gases at 0.25 cross 0.25 degree horizontal resolution. Another instrument, tropospheric emission spectrometer, commonly known as TESS. It is on board Aura spacecraft. Its spectral coverage is 3.2 to 15.4 micrometer. It provides vertical profile of ozone, carbon monoxide, methane, etc. TESS level 3 product provides global distribution of gases at 2 cross 4 degree horizontal resolution. So now we will study trace gas distribution over Indian subcontinent and what are the atmospheric processes which are affecting the distribution of these gases. So here in this plot, monthly distribution of tropospheric columnar NO2 is shown over the Indian subcontinent, which is obtained from ozone monitoring instrument for year 2008. This plot is shown from December, January, February to September, October and November. This plot shows that total columnar content or tropospheric columnar content of nitrogen dioxide is high during December, January, February, March, April, May and June. And after that, this value becomes lower and it remains lower till September. After that, again, October and November values are higher. Similarly, we have also investigated distribution of carbon monoxide by obtained from tropospheric emission spectrometer at 825 hectopascal. This also shows similar type of feature in which January, February, March, April and May values of carbon monoxide are high. June, July, August and September shows lower value and again October, November and December shows higher value. Then what is the reason why we are getting high value during January to May and again from October to December, and why we are getting lower value during June to September? So there are two types of possibilities which we have already read. One, atmospheric boundary layer dynamics, and the second is transport. Effect of atmospheric boundary layer and transport can be studied when we take specific cities. So we have taken 4 cities over India. Those are Lucknow, Kolkata, Ahmedabad and Jaipur. Again, like the special plot, this plot also shows high value during winter and low value during summer. To explain why we are getting this type of variation, we have calculated back trajectories. Back trajectories are nothing but the latitude and longitude information back in time of an air parcel which is present on one particular day over the observational location. So for this we have used high split back trajectory model, by using which we can calculate location of air parcel back in time. If we want to know what is the location of air parcel today, then we can track it back. Suppose one air parcel is present over Dehradun today, then what was its location before one day? what was its location before today, and so on can be calculated using trajectory models. So in this plot, we have taken 7 days back trajectory over Lucknow, Kolkata, Ahmedabad and Jaipur during December, January and February. These plots shows that in all these locations are receiving air parcel from the continental region, either from Middle East or Pakistan, and or it is circulating over the Indian region itself. However, during June, July and August, these air parcels are arriving from oceanic region, from Indian Ocean via Arabian Sea. So this shows that during winter time, we are receiving air mass from anthropogenic polluted locations, whereas during summer time, we are receiving air parcel from the cleaner marine region. When air is coming from cleaner marine region, it is not carrying any pollution. It is clean and it is diluting the air parcel and diluting the value of pollution over the observational location. Again, second process which can affect the distribution of these pollutants is atmospheric boundary layer. So atmospheric boundary layer depends on the heating of the surface. When the heating of surface is higher, the atmospheric boundary layer can go deeper in the atmosphere. During summer time, when sunlight is high, that time boundary layer can go deeper in the atmosphere and the pollution which is emitted near the surface will get mixed up within the larger volume. However, during winter time, boundary layer height is low, and during that time the pollution is trapped in the lower volume. And when pollution is trapped in the lower volume, the concentration of pollution will elevate. Because of these two processes, we are getting this type of monthly distribution. However, we are getting different type of distribution for ozone. Ozone does not show much high value during January and February. Values are much higher during March, April, May and partially in June. And after that, July, August and September values are low. And again, value peaks the pollution and increases during October, November and December. Then why this ozone is showing different feature? Why this ozone is showing high values during March, April and May? Because ozone is a secondary pollutant. It is dependent on the precursors. And though precursors are high during winter time, but sunlight intensity is not that high. And ozone is produced through photochemistry. So when sufficient amount of pollution in precursor pollution and solar light is available, then only high level of pollution is observed. So ozone shows high value during pre-monsoon season or spring season or March, April and May. Ozone depends on sunlight also. Ozone depends on several gases also. So we cannot take ozone as a direct pollutant for the study of emission of pollution. So for that we have taken carbon monoxide distribution over east coast and west coast of India to see how pollution varies in the east coast and west coast, how Indian region is different over west coast and east coast. For that we have taken MOPIT data over these locations which are highlighted by black points. These are the observational locations, and over these locations we have taken data for 10 years and we have analyzed that. And here in this plot, these average data are plotted with respect to latitude. And this clearly shows that for latitude less than 15 degree north, values are almost comparable across the India. However, there is a big difference between east coast and west coast when we see variation for latitude more than 15 degree north. What is the reason? Because high level of pollution is being injected from Indo-Gangetic plain. Again, to get information about the difference between the pollution over east coast and west coast, we have analyzed the monthly distribution of carbon monoxide over east coast and west coast. And we have seen the difference is significant for each month except during June, July and August. And difference is maximum during pre-monsoon season during March, April and May. So this analysis shows that latitudinal variation of columnar CO high value shows of carbon monoxide pollution over the northern part of Bay of Bengal, and monthly variation of CO shows significantly high amount of CO over the east coast with respect to west coast. Satellite data can also help on the when we get high level of pollution in the atmosphere and how that pollution plume is traveling from one location to other. So here is an example, sulfur dioxide emission from volcanic eruption. In this plot, total columnar sulfur dioxide is shown and it is in Dobson unit, and it is analyzed over these locations: Ludhiana, Delhi, Kanpur, Durgapur, Kolkata, Guwahati, Ahmedabad, Nagpur and Chennai during January 2005 to December 2010. During these many years, we have seen very high value over Ludhiana, Delhi, Kanpur, Durgapur and Kolkata during November 2008. Why we are getting very high value during this period? This we wanted to analyze. For this, we have analyzed daily variation of sulfur dioxide column values from the OMI data during 30th of October to 12th of November. Over these 5 locations where we have observed very high amount of sulfur dioxide during this particular month. And we found that there was very high amount of sulfur dioxide columnar concentration during 4th of November to 8th of November. What was the reason of this very high amount of sulfur dioxide? This we have investigated when we have taken spatial distribution of sulfur dioxide. For this, you can see here in this plot, one volcanic eruption is occurring, and because of that, a high plume of very high intensity, very high concentration of sulfur dioxide is emerging. It started on 4th of November, and this plume eventually got transported to Indo-Gangetic Plain. On 4th of November, this was the location of plume. On 5th of November, it transported via Saudi Arabia and Iran towards the Indo-Gangetic belt. On 6th of November, it started dissipating, and 7th of November, it is not there. So this shows the distribution of any pollution. If we analyze the spatial distribution of any pollution, we can identify the source location of high level of plumes, and we can track the pollution, how pollution emerged in the atmosphere and how it got dissipated. Again, we study extreme CO pollution episode due to forest fire. For this, one extreme CO pollution event occurred over Indonesia during November 2006. The background picture shows high level of carbon monoxide over this region. This is the Indonesian region. So for the analysis of this event, we have taken 10 years of MOPID data. MOPID data from 2000 to 2010. We have taken a rectangular belt over Indonesia, which is bounded by latitude 4.5 degree north to 4.5 degree south and longitude 87.5 degree east to 118.5 degree east. So this is the region which we have defined, and we have taken average over this location for every month since starting from 2000 to 2010. And we analyzed this data, carbon monoxide data, at pressure level 500 hectopascal, 400 hectopascal and 300 hectopascal. We have analyzed time series of this, and we found that values are significantly very high during October-November 2006. What is the reason? If you do see the values, it is more than 200 ppb high, which is very large amount in the free troposphere where there is no source of carbon monoxide. So this is a very prominent event occurred which is observed by MOPIT. So we tried to identify the source of this pollution using fire hot spots and total columnar content of CO during 2006. So in this plot, month and year is shown on x-axis, and y-axis shows fire hot spots which is obtained from advanced along track scanning radiometer during that period on daily basis, and that are calculated over the Indonesia region, which we have defined in the first slide of this event, and we have plotted it with monthly average columnar CO. If you view this plot closely, you will see that total columnar CO closely follows the variation of fire hot spots, and it showed elevated level during October and November when fire hot spot shows maximum value. So from here we can suspect that this event was associated with biomass burning over Indonesia. But we can only suspect. Can we say that exactly because of this only high level of pollution event occurred over Indonesia? Yes, but not only using satellite data, but using chemistry transport model. We have utilized model for ozone and related chemical tracers, MOSART. This is a global offline three-dimensional chemistry transport model, and we have utilized version 4 of this. This model mathematically computes the atmospheric chemistry and dynamics. For this model requires meteorological field, ANSEP data, meteorological field, and emission of pollutants which are taking participation in the photochemistry and chemistry of the atmosphere. For that we have taken emission from emission inventories. These are POET emission inventory, which gives the global anthropogenic and biogenic emissions. RIAS emission inventory, which gives the information about Asian anthropogenic emissions, and global fire emission database GFET emission inventory, which gives the monthly fire emission all over the globe. So these emissions and meteorological data are analyzed by this model. This model mathematically computes how the atmosphere is chemically evoluting. This model simulates 85 gas phase species, 12 bulk aerosol compounds, 39 photolysis, and 157 gas phase reactions. The horizontal resolution of this model is poor, not very good, because it is a global model. So it is 2.8 cross 2.8 degree horizontal resolution, and vertical coverage from surface to around 2.7 hectopascal at 28 sigma pressure levels. This model calculates continuity equation for different gases to see the evolution of that gas in the atmosphere. As this model is mathematical model, it step by step calculates effect of horizontal movement, effect of vertical movement, and effect of chemistry. So we have utilized this model with this emission inventory and meteorological data, and we have tried to simulate the same atmospheric phenomenon which is happening in real. So this figure shows carbon monoxide pollution episode using satellite data MOPIT and chemistry transport modeling MOSART. So left hand side figure shows MOPIT distribution, measurement of pollution in the troposphere during October 2006 at 500 hectopascal per millibar, and downside figure shows MOPIT measurement for October 2006 at 300 millibar. Right hand side figure shows the same thing but simulated by Mozart. This is real-time observation. This is calculated by model, and this model is simulating atmospheric chemistry by taking emission inventories as well as meteorology. So extreme carbon monoxide pollution plume event occurred over Indonesia is very well reproduced by chemistry transport model Mozart. You can see that values are high over this region. This is also reproduced by our model for both the pressure levels. This indicates that our model can be taken as reliable. Yes, our model is considering everything correctly. It has taken correct emissions. It has simulated the atmospheric chemistry correctly. So we can rely on our model. Then we can, because model is a mathematical simulation, we can take information, we can take out other information from model which we cannot take out from the satellite data. What are these additional information? These additional informations are effect of different atmospheric processes. Like satellite data will tell you that this is the pollution distribution over this location. This is satellite data can give information that suddenly over this region we have received very high amount of pollution. But satellite data will not tell any information about the specific source and amount of contribution coming from that source and what is the contribution from different atmospheric processes. But model is simulating everything mathematically. So it is taking effect of horizontal motion. Again, it is calculating effect of vertical motion. Again, it is calculating effect of transformation of chemical species. And then it is simulating atmosphere. Then this model can give you information about the different processes, and it can give you information that how much of pollution is being added or removed by different atmospheric processes. So for this we have taken mass diagnostic analysis of model, and x-axis shows date, and it varies from September 2006 to December 2006, and y-axis show carbon monoxide weight, which is introduced at 500 hectopascal because of convection, advection and chemistry. It shows that over Indonesia region, here I would like to remind that Indonesia region is average region which we have defined in first slide. Over that region, how the effect of convection is varying. So it is showing that because of convection, this red color variation shows the effect of convection, and it shows that carbon monoxide is enhancing over 500 hectopascal because of convection. The contribution of convection is positive, whereas contribution of advection is shown negative. So this indicates that because of convection process, the carbon monoxide is increasing over 500 hectopascal, whereas because of advection process, the amount of carbon monoxide is decreasing over this region. This indicates that near surface enhanced this biomass burning event occurred, and because of convection, this this emission got transported over high altitude at 500 hectopascal, and over that region advection started occurring, and because of that the pollution plume got dissipated slowly with time. And here again an additional information is also introduced, that is chemistry. If you see, contribution of chemistry is almost negligible. It is always zero. This means chemistry is not occurring at this altitude. There is no role of chemistry, only convection and advection are playing role for this distribution. So this is a very important information which is given by our model, which cannot be taken from the satellite data. Again, I told you that the model simulation is mathematical simulation, and it takes the emission inventories into picture. It takes the emission near the surface. It takes the meteorology also, and it allows the atmosphere to change from its initial condition. In this process, as we are giving emissions separately, we can take out the emission from this, and we can also see if there is no emission, how a particular pollution will vary in the atmosphere. So we have run this model in two scenarios, one with emission and second without emission. In first process, we have switched off emission, we have taken normal run, and in second process, we have switched off emission over this particular region. Only emission because of biomass burning. And we allowed our model to evolve in the atmosphere, and it should start from the beginning, and it should consider all the atmospheric phenomenon, all the emission, but without biomass burning which occurred over Indonesia. Then we have two graphs. One is the vertical distribution of carbon monoxide, these red curves over this Indonesia region, and one without emission. When there is no emission, what would have been the vertical distribution of carbon monoxide? That is also simulated by this model. So model run with two scenario, one with biomass burning emission over Indonesia region, other without this emission. So the difference at each level can be calculated. We know that because of model, we can calculate that at each pressure level, how much amount of carbon monoxide is being added. And the average is taken from surface to 100 hectopascal, and we have found that average CO enhancement is around 104 plus minus 56 ppbv. So we can quantify the contribution, we can identify the source, we can quantify the contribution when we utilize model. But model alone cannot work. We need satellite observations also for the validation of model. So it can give you very important information when you analyze satellite data along with chemistry transport model. So conclusion, satellite-based measurements provide spatial distribution and temporal evolution of air pollutants all over the globe. These measurements can give important information about the extreme pollution episodes. Analysis of satellite-based observations together with chemistry transport model simulation can depict a 3D evolution of a pollution plume and identify the atmospheric processes responsible for these events. Thank you.